Hello again, ladies and gentlemen. This is the second video lesson reviewing our practice exam on behavior of matter. It's going to pick up with question number 9 and move forward. There'll be a third video right after this. Again, we are looking to review this exam, 20 questions on behavior of matter. All right, question number 9. The diagrams below represent three 1-liter containers of gas, A, B, and C. Each container is at STP, which is standard temperature and pressure, so they're under the same conditions. Which statement correctly compares the number of molecules in the container? So we have helium, 1 liter at STP, O2, oxygen gas, 1 liter at STP, and CO2 gas, 1 liter at STP. This illustration may be of some assistance. Here it is. Straighten that out. And in this illustration, it's showing that we have argon, oxygen, and nitrogen, each same volume, different masses because they're different substances, each containing 1 mole of the substance under the same pressure and same temperature, so under STP. And what do you notice that relates to this question? Number of molecules, the quantity. Are they different? No. And Avogadro's hypothesis said that under equal conditions, the same volume of different gases will have the same number of molecules. Choice number 4. Let me grab my pen. Choice number 4. Alright, number 10. A rigid cylinder with a movable piston contains 2-liter sample of neon gas at STP, standard temperature and pressure. Those have values assigned to them. I'll show you those in a moment. What is the volume of this sample when its temperature is increased to 30 degrees Celsius, while its pressure is decreased to 90 kilopascals? Let's just take a look at a picture and see what it's trying to get you to visualize. Now, this is not a perfect picture, but on the left you will see that we do have a movable piston that has a gas that is compressible in there. Those black dots represent gases. On the right side you will see that this gas was compressible. And what this is showing you is that the temperature has been changed and what occurs. So as the pressure as it gets compressed, as the volume decreases, the temperature goes down. As the temperature increases, the volume goes up. Now we have 3 variables changing in this question, and with those 3 variables being temperature, pressure, and volume, let's explore what formula we should use. And when you take a look at the reference table, you will see the combined gas law right here, P1V1 over T1 is equal to P2V2 over T2, where pressure, volume, and temperature are what are being altered and represented here. Let's get that out of the way. We now know that that formula is going to be at use. We also know that in this question it talked about STP. Let's take a look at what that is. Standard temperature and pressure relates to these values here. Standard pressure could either be 101.3 kilopascal or 1 atmosphere. There are other measures, but these are the ones that we are asked to use. In fact, this question says use kilopascal. Standard temperature, we could choose either 273 Kelvin or 0 degrees Celsius. The gas laws require the use of require the use of Kelvin. And given that our question says 30 degrees Celsius, we are actually going to have to roll back to this one once again and look at this. We are going to have to convert those Celsius into Kelvin. So let's do this. Let's identify what we know in this problem. We know that we are using the formula, okay, P1 V1 over T1 is equal to P2, squeeze in here, V2 over T2. So what are these values? Do we have a P1? P1, oh, standard pressure, 101.3 kilopascal. P1, do we have a V1? Do we have a starting volume? We do, 2.0 liters. And do we have a T1? We do, once again, standard temperature, which is 273 Kelvin. Now, do we have a P2? Yes, 90 kilopascal. Do we have a V2? Well, it says, what is the volume? We do not have a V2. Do we have a T2? T2, 30 degrees Celsius. But what do we have to do to convert it into Kelvin? We have to add 273. So we are using a value of 303. Let's build the equation so we can get a final answer. So we have 101. Let's undo that. 101.3 kPa times 2.0 liters over 273 Kelvin is equal to, what is our kPa? 90 kPa times our V2 over 303 Kelvin. Now if you cross multiply and divide, you will ultimately get an answer that gets rounded to 2.5 liters. Question 11. Base your answer to the following question on the graph below. The graph shows heat being added at a constant rate to a substance A and to substance B, which begin as solids below their melting point temperatures. Solids, liquids, gases. The question, compare to substance B, substance A has. So what is true about substance A versus substance B? Here is a quick review of a heating curve. It is at this point, right here, that a solid becomes a liquid. So here we are talking about melting. It is at this point here that a liquid becomes a gas. So we are talking about vaporizing or even boiling. Let's reduce this. Now, which of these statements is true? Is substance A, or does substance A have a lower melting point than substance B? Substance A. It does have a lower melting point. Does it have a lower boiling point? Nope. Does it have a higher boiling point? Yep. The answer for this one is choice 2. Question 12. Now these gave everyone fits. Let's go through it. The temperature of a 100 grams of water changes from 16 degrees Celsius to 20 degrees Celsius. What is the total number of joules of heat energy absorbed by the water? So we're talking about an energy change. We are talking about our formulas related with heat. Let's take a look at them. Here they are. Q is equal to mc delta T, where delta T means change in temperature, C is specific heat capacity, M is mass, and Q is heat. Q is equal to M, mass, times HF, heat of fusion. Let me move this over. Heat of fusion. Fusion occurs when a substance melts. So going from a solid to a liquid, or the same amount of energy is necessary to reverse it, but will be released. Or are we talking about Q is equal to the mass times the heat of vaporization? The amount of heat necessary to convert a liquid into a gas to vaporize it. Just so you know, if you reverse the process, again, that amount of energy would be released. So, does the question talk about a change in temperature, a change in state of matter between solid and liquid, or a change in state of matter between liquid and gas? It's going to be the first one. Let's get this out of the way. Okay. Now, that formula was Q is equal to MC delta T. Okay. Which of these variables do we know? We know the mass. The mass is 100 grams. Do we know what C is? Yep. C is a specific heat capacity, and it can be found right here. 4.18 joules for every 1 gram changing 1 Kelvin. Let's get this out of the way. 4.18 joules per gram Kelvin. And do we know what the change in temperature is? From 16 degrees Celsius to 20 degrees Celsius is 4 degrees Celsius change. Interesting point. This unit is Kelvin. But what's nice is when you change 1 degree Celsius, you are also changing 1 degree Kelvin. So we could actually swap out degrees Celsius for Kelvin. Multiply these together, and there is your answer. Alright, this one is straightforward. At standard pressure, which element has a melting point higher than standard temperature? What is standard temperature? Standard temperature is either 273 Kelvin or 0 degrees Celsius. So which of these substances relates? We would go to table S and investigate, because on table S we have boiling point, melting point, electronegativity, and so forth. We're talking about melting point. Now, fluorine, F2, where are you? There you are. Melting point, 53. Is that above 273 Kelvin? That's the unit we're using. No. Bromine, where are you, bromine? Are you there? There you are. Bromine. 266. Close? No cigar. Iron. 1,811 Kelvin. Far above the melting point, the temperature, standard temperature. Answer is 3. Question number 14. The phase change represented by the equation iodine solid is changing to iodine gas. Now, what is missing in this step? Well, you would typically see that iodine, what should belong here, might actually turn into I2 liquid first. Well, in this case, that's not happening. And here is an example of a similar thing that happens when carbon dioxide is a solid and exposed to the atmosphere. It goes straight to a gas. You may have seen something similar to this at a Halloween party or what have you. This is dry ice just exposed to the atmosphere, and you get this bubbly looking gas form that is denser than air, so it just rolls over the edge and then creeps out to just expand, because that's what gases do. So what do we actually call this? Well, this is called sublimation.